Hi everyone, I'm Simone Benella from the Institute for Space Astrophysics and Planetology in Rome, and in this presentation I like to talk about galactic cosmic ray Forbush decreases as observed on board the LISA Pathfinder mission and the space weather capabilities of the future LISA mission. The aim of this work is to present main results obtained with the study of galactic cosmic ray flux variations with the LISA Pathfinder particle detector data. This study is important for the future LISA mission since one of the key disturbances affecting test masses on space-based gravitational wave detectors is the charging process induced by penetrating cosmic ray particles and their secondaries. An estimation of the average shot noise for the LISA Pathfinder mission was carried out, but recently the European Space Agency has found it necessary to take into account galactic cosmic ray variations in order to better understand the measured noise spectrum. Interactions between cosmic rays and the interplanetary medium generally produces a stationary galactic cosmic ray flux on both long term, that means years, and short-term time periods like hours or days. Moreover, the flux might become non-isotropic, especially during sporadic events like Forbush decreases that are caused basically by the passage of energetic interplanetary coronal mass ejections. Galactic cosmic ray observations on board the LISA Pathfinder were important to better understand the test mass charging processes, but provided important constraints also for space physics studies. In this talk I will summarize what we learned from the LISA Pathfinder mission, and I will talk about the possible future scenario for the LISA mission. Galactic cosmic ray intensity variation are due to the interaction between cosmic rays and solar heliospheric processes on different timescales. They can be divided into two groups. We have long-term and short-term galactic cosmic ray variations. The long-term variations are those modulation occurring in response to the 11-year solar activity cycle and the 22-year global solar magnetic field polarity reversal. On the other hand, short-term variations are galactic cosmic ray modulation lasting less than 1 Bartels rotation, that is a period of 27 days, corresponding to the average time period of one synodic solar rotation. And this kind of modulation in cosmic rays are related basically to solar wind disturbances. Galactic cosmic ray short-term variations can be also divided into two parts. We have recurrent variations and transient variations. Recurrent variations are associated with high-speed solar wind streams from coronal holes that represent basically structure on the Sun slowly evolving over several solar rotation periods. While transient galactic cosmic ray short-term variations are associated with sporadic events. The most important are, as I said before, interplanetary coronal mass ejections producing Forbush decreases. Forbush decreases are sudden drops in galactic cosmic ray intensity followed by a smooth recovery phase. They are caused by the passage of interplanetary coronal mass ejections, and I reported here quite popular sketch of an interplanetary coronal mass ejection by Richardson and Kane. And in this picture you can see the main phases of the interplanetary coronal mass ejection transit, and the first is the interplanetary shock followed by the turbulent sheet region, so-called turbulent sheet. This is a region of compressed and highly fluctuating plasma, and the inner core of the ICME is basically the magnetic cloud that is a closed plasma structure presumably connected to the Sun. So in this slide is reported the LISA Pathfinder particle detector time series from February 2016 through July 2017, and the particle detector measured proton and helium nuclei with energies above 70 MeV per nucleon, with an acquisition rate of basically 15 seconds. Data were hourly averaged in order to reduce the statistical uncertainty on a single data point to the 1%. The increasing in galactic cosmic ray long-term data trend was due to a decreasing solar activity, since the period of time of this data corresponds basically to the descending phase of the solar cycle number 24. Other variations superimposed to the long-term data trend represent galactic cosmic ray short-term variations. And we found 45 recurrent variations, 23 transient variations lasting less than 2 days, and 3 Forbush decreases on the whole dataset. In order to study galactic cosmic ray flux recurrent short-term variations, we performed an analysis of periodic components of the whole time series. Since the signal is clearly non-stationary, we adopted the Hilbert-Wang transform to analyze the particle detector data, and by decomposing the dataset in modes, we found that periodicities related to the synodic solar rotation period of about 27 days and higher harmonics are present. This is also evident by computing the marginal Hilbert spectrum that are reported here on the right, where we observe an increase in power in correspondence of frequencies associated to the solar rotation periodicities. We observe also 1/f power spectrum over about 1 decade up to 10 to the minus 5 Hz. So LISA Pathfinder observed 3 Forbush decreases associated with interplanetary coronal mass ejections. The first 2 were observed during the Bartels rotation 2496 reported here. Forbush decreases are reported between these vertical lines. First one was on July 20th, 2016, second one on August 2nd, 2016. I reported also contemporaneous measurements. These are LISA Pathfinder particle detector observation. These 3 panels are some parameters, interplanetary magnetic field and plasma measurements from the ACE experiment in that one. The third Forbush decrease was observed during the Bartels rotation 2507, exactly on May 27th, 2017. The most intense event was the August 2nd Forbush decreases. In this slide, I would like to report part of the detailed study we did on this Forbush decrease event. The total Forbush decrease amplitude was of about 9%, as you can see here, 6% during the first part of the ICME and 3% during the second. The second structure within this ICME is a magnetic cloud, and we reconstructed the configuration of the magnetic field of this event by using an advanced data analysis technique called Grad-Shafranov reconstruction. To do this reconstruction, we used wind data at L1, and this is the outcome of the reconstruction. Basically, we have an axial magnetic field structure. The Z component is reported by the color, is indicated by this color map, and the potential vector level curves are reported in black. I reported also the LISA Pathfinder in Chine and wind spacecraft paths through this magnetic cloud. This magnetic field configuration allowed us to perform a test particle simulation by using protons in the energy interval between 70 MeV and 100 GeV. Protons represent roughly the 90% in composition of galactic cosmic rays in the inner heliosphere. The simulation outcome was basically a proton intensity variation, and if we compute this proton intensity variation along the LISA Pathfinder path, we get this result reported in red. So this profile is compared here with galactic cosmic rays observations directly from the particle detector on board LISA Pathfinder, and we can see that the perfect agreement between model and data allowed us to validate the method by using LISA Pathfinder observations. Moreover, by interpolating the magnetic field obtained from the Grad-Shafranov reconstruction along the LISA Pathfinder trajectory, we got the 3 interplanetary magnetic field components during the magnetic cloud crossing. and they show an excellent agreement with LISA Pathfinder interplanetary magnetic field observations. Data from LISA Pathfinder magnetometers reported in these pictures were processed by Andrea Cesarini, and I recommend to see his talk for more details on this topic. So this work allowed to demonstrate the importance of the galactic cosmic ray observations on board LISA Pathfinder in the analysis of galactic cosmic ray short-term variations that resulted to be important for a better understanding also of test mass charging process and also for space weather related topics. The small number of Forbush decreases observed on board LISA Pathfinder depends on the fact that the mission lapse time was characterized by a near solar minimum activity. In this plot are reported the number of Forbush decreases observed at the Earth barrier as a function of time, and the red superimposed line is the solar sunspot number that is usually used as a proxy for the solar activity level. It is clear that the occurrence of Forbush decreases is correlated with the solar activity, since during solar maximum the production of energetic interplanetary coronal mass ejections is larger. And the LISA mission is scheduled for launch in 2034, and it will cover the solar maximum of the cycle 26, and thus a large number of Forbush decreases is supposed to be observed on board the 3 satellites of the LISA mission that can be also important for space weather studies. Indeed, one important space weather parameter is the Forbush decrease amplitude during ICME transit. In this figure are reported 2 scatter plots between Forbush decrease amplitudes observed at the Earth and 2 parameters of the corresponding ICMEs, the maximum magnetic field and the maximum solar wind speed. The correlation coefficient is about 0.6 for both parameters, and in this case the amplitude of Forbush decrease is computed by using the global latitude survey method, because neutron monitors at different geographic position allow to observe different galactic cosmic ray energies, being Forbush decreases energy dependent processes. Contemporaneous observations of 3 processes from the 3 LISA satellites would be useful to get precious insights on the physics of Forbush decreases. About space weather science, it is well known that Forbush decrease amplitude is in most cases correlated with the DST index, that is an equatorial index that quantifies basically the geomagnetic disturbance level. To summarize, LISA Pathfinder hosted a particle detector with a high geometrical factor, allowing for low statistical uncertainty measurements for both galactic cosmic ray, diagnostic and scientific studies. The hourly average data presented 1% statistical uncertainty. We analyzed 45 recurrent flux modulations due to the interaction with high-speed solar wind streams, 3 Forbush decreases caused by the transit of interplanetary coronal mass ejections, and 23 transient variations lasting less than 2 days, small variations that are associated with minor interplanetary disturbances, mainly heliospheric arrow sheet crossings. All these events can affect the test mass charging process as a function of time, and for this it is important to host on board the future LISA mission particle detectors with sufficient statistics on the higher energy integrated channel. I'd like to recommend you to follow the talk by Catia Grimani on this topic. On the other hand, the Forbush decrease amplitude is considered to be an important and promising parameter in space weather studies. From the statistical studies based on the Global Neutron Monitor Network observations, a good correlation between the DST geomagnetic index and the Forbush decrease amplitude is clearly present. And space-based observations are crucial to better understand also the physical properties of Forbush decreases at lower energies, as well as their dynamics. Finally, contemporaneous observation of Forbush decreases with the 3 LISA satellites and together with the Neutron Monitor Network will allow to study the energy dependence of these events. So That's it for my presentation. I'd like to thank you for your attention.